Hello, everybody, and welcome to the Force of Gravity Part 2, or the Universal Law of Gravitation. This was the last lesson of our dynamics unit, but I've added one more on, so this is our second to last video. All right, so we've done a little bit with gravity in terms of Fg is equal to mg. But what we're going to do now is look at gravity not on the Earth's surface. So we know that gravity attracts any two objects depending on their mass and distance apart. So whenever we do gravity problems with Fg is equal to mg, the other mass that we're talking about is the mass of the Earth. And we use that g constant based off of the mass of the Earth and the radius of the Earth. And that's why we can calculate that force of gravity. But as soon as we are out in space or really far above the Earth, things get a little bit different. So the formula looks something like Fg is equal to big G multiplied by, let's do m1 multiplied by m2 all over radius squared. So in this case, we can label all of these. Just give me 1 second. There we go. So we have Fg is obviously force of gravity. And that is in newtons. Big G is the gravitational constant. So this is just a constant. It's on your formula sheet, I believe, or your constant sheet, which is, I think, your unit sheet that I handed out at the start of the class. So that is 6. Well, let's label it. Gravitational constant. And this is always the same no matter where you are. That is 6.67 times 10 to the negative 11. The units, if you care, are meters cubed over kilograms seconds squared. That's a weird one, I know. Or actually, you know what? It's better to write the units as newtons meters squared over kilograms squared. Same units. I mean, it doesn't matter. They're designed to cancel a bunch of the other things out so that when we calculate the force of gravity, we're left with newtons. M1 is mass of first object, and obviously that's in kilograms. M2 is mass of second object. That's also in kilograms. And R is the distance between the masses. And that's the center. The center of the masses. And you can see R is squared. So the trickiest part with this formula is that a lot of times you're dealing with scientific notation, and that can lead to some issues just calculating. So just be careful when you're typing things into your calculator that you're using brackets, you're using your bed mass, and just double checking things if you're not sure. So let's get some practice with this. What is the force of gravity exerted on a 70 kilogram astronaut that is standing on the Earth's surface? So we have a couple of things that we don't need to memorize. We have the radius of the Earth, and we have the mass of the Earth. So we can actually do this problem using Fg is equal to mg, but just in order to get some good practice, we will do it with the big force of gravity formula. So Fg multiplied by m1, m2 over r squared. So in this case, we have r, we have m2. We can also say that the mass of the astronaut, we'll make that m1, is 70 kilograms. And we have g, that's the universal gravitational constant. So let's plug everything in. We know that's going to be, big G is 6.67 times 10 to the negative 11. At m1, that can be the mass of the Earth, 5.98 times 10 to the 24 kilograms. And then obviously the mass of the astronaut is 70 kilograms. And then we can divide by r squared. So 6.38 times 10 to the 6, and that's all squared. People tend to forget that, so be careful. That's all squared. So you just have to type all this in your calculator. It can be a bit tricky when you do that, so just be careful. But if you type all of this in, you should get 686 newtons. Yay. All right. What is the force of gravity on the same astronaut? I'm going to write this down before I forget. 70 kilograms, who has at an altitude of 6.38 times 10 to the 6. All right, so let's draw this. So we have the Earth. Let's make a bigger Earth. We have the Earth. The radius of that Earth is 6.38 times 10 to the 6 meters. And that astronaut is at an altitude of the same. So another radius is worth. There's your little astronaut there. He's at an altitude of 6.38 times 10 to the 6 meters. So a couple different ways you can do this. To find the distance between the centers of the masses, you need to calculate the distance from here to here, which is basically 2 times the radius. So you can say the distance is going to be 2r, or you can say it's going to be r plus r. It's completely up to you. You're going to get the same answer. So let's plug that in. Fg is equal to g m1 m2 over r squared. And we can plug our numbers in. So we know g, 6.67 times 10 to the 11. You're going to use that, 10 to the negative 11, sorry. You're going to use that a lot. The m1, mass of the Earth, again, 5.98 times 10 to the 24. You'll use that quite a bit too. Mass of the astronaut, 70 kilograms. And now the distance between is going to be, so you can do it something like this if you wanted, 2 times 6.38 times 10 to the 6, and then that's all squared. So this inside this 2 times the radius of the Earth has to happen before you square everything. And that's why I'm using these different brackets here, these square brackets and circle brackets, just so that I can keep my brackets in order. All right, so if you do all of that and you type it into your handy dandy calculator, you should get 171 newtons. So that makes sense. The force of gravity should be less as the astronaut gets further away from the Earth. Hopefully that makes sense. So another way to think about this, okay, so this is going to be something that we're going to do a bit of, and we'll talk more about it in class. But if we look at this formula, everything is kind of related. So for example, if mass 2 goes up by a factor of 2, that means my force of gravity is going to go up by a factor of 2. Hopefully that makes sense. If mass 1 also goes up by a factor of 2, then force of gravity is going to go up by a factor of 4. Those are proportional. As the mass goes up, the force of gravity goes up. Hopefully that makes sense. But, okay, it won't let me scroll. My computer's frozen. There we go. Everybody panic. Because the radius is on the bottom of this fraction, it's inversely proportional. So let's write this. Proportional, if I can spell. The masses, Fg and m. The radius and the force of gravity are inversely proportional. I think this is called directly proportional. Sorry, just trying to make sure I got my lingo correct. The radius and the force of gravity are inversely proportional. So that means as radius goes up, Fg goes down. As we increase the distance, the force of gravity goes down. And that makes sense. But we have to be careful. So basically, as force of gravity goes up, or as radius goes up, force of gravity goes down. And as radius goes down, force of gravity goes up. They act opposite on each other. But you have to be careful because the radius is squared. So in this case, if we make the radius go up by a factor of 2, the force of gravity is going to go down by a factor of 2 squared because of that squared. So it's going to go down by a factor of 4. So if I double the radius, or the distance between the two objects, the force of gravity is going to go down by a factor of 4. So if we look at that astronaut on the surface of the Earth, his force of gravity was 686 newtons. And then once we doubled the radius, this is 2r now, this was r. Once we doubled the radius, his force of gravity was 171, and we calculated both of those. And you can see that 171 is 1/4 of 686. So we doubled the radius, which means the force of gravity should have gone down by a factor of 2 squared, or 4, which it has. 171 newtons divided by 686 newtons is 1/4, 1/4. Hopefully that makes sense. We're going to use this quite a bit, so you'll get used to it. For example, right here, an astronaut weighs 800 newtons on planet X. How much would she weigh if she was at an altitude equal to the radius of planet X? So on planet X, she weighs, well, let's do this, m1, m2 over r squared. So her weight, which is force of gravity, be careful, weight is force of gravity, not mass. Her force of gravity is 800 newtons. Now what we're going to do is we're going to double the radius, right? Because she's going to go up to an altitude equal to the radius, which means that she started on the planet, and that was 800 newtons. And now she's going to go up to, so let me finish that, a distance of equal to the radius above the surface, which is 2 radiuses from the center. So we can write this as g m1 m2 over 2r squared. And we can rewrite that as g m1 m2 over 4r squared, right? That 2 is squared. So now what we've said is g m1 m2 over r squared is 800. So we can actually say, well, that's the same thing, so that should equal 800. So really what we're doing is 800 divided by, we got 4 left. So we know that the force of gravity is 200 newtons. the radius went up by 2, the force of gravity went down by a factor of 2 squared, which was 4. Inversely proportional. Hopefully that makes sense. A spaceship orbits a planet at radius r and weighs 10,000 newtons. How much would it weigh if it orbits a planet twice as massive at half the radius? All right, so the way I like to do this is I like to write my formula. Fg is equal to, oh, I forgot one. G m1 m2 over r squared. All right, so we know this is equal to 10,000 newtons. So now what's going to happen? Well, the spaceship is going to orbit a planet twice as massive. So that means one of the masses is going to go up by a factor of 2. That means my force of gravity is going to go up by a factor of 2. And then it's going to go half the radius. So the radius is going to, let's use a different color. The radius will go down by a factor of 2. It's getting halved, right? So it's going down by a factor of 2, which means force of gravity has got to go down by a factor of 2 squared, which is a quarter. So let's do this in steps. This is my favorite way to do this. So force of gravity, if I'm doing the purple step, has to go up by a factor of 2. So I'm going to multiply that by 2, and I get 20,000. Oh, look what I did. Let's pause. I screwed up here. You probably already caught it. My force of gravity goes, my radius goes down by 2. That means here, right here, this needs to go, let's flip vertically, up by a factor of 4. There we go. It needs to go up by a factor of 4. They're inversely proportional. I got a little bit screwed up there. So now we're at 2,000 newtons. I was looking at it and like, my answer's not going to make sense. So now we have 20,000 newtons. And that also has to go up by a factor of 4. Let's finish it off in blue. So now I have 80,000 newtons. That's my new force of gravity. That's the easiest way to think of it. I think, yeah, there's other ways. If this doesn't make sense for you, I can help you out with that. Let me know. It's just a matter of figuring out how your brain works and finding a process that works for you. Cool. So that's kind of it. You have to be able to use the formula Fg is equal to Gmm over r squared. And you also have to be able to look at the relationship between the values, right? As m goes up, Fg goes up. They are directly proportional. And as r squared, or as the radius goes up, the Fg goes down by a factor of that squared. So they are inversely proportional. And then you have that squared as well. That adds a complication. But hopefully that makes sense. Thanks for watching. Don't forget to like and subscribe.